Lesson 1 says, what is physics? I first started teaching physics Madison in 2003. I told my mom, I'm teaching physics 12. And she was, well, you know, Calvin, you taught math for your first few years, and I know what math is. What the heck is physics? And I couldn't really give her a great answer. I'm going to steal as an answer what my university prof said to us. He said that physics was the science of measurement. He said that any time you were measuring or analyzing or calculating in science, you were doing physics. Now, I like that definition because it swallows up every single other science. If you're measuring atoms in chemistry, that's not chemistry, that's physics. If you're measuring cells in biology, that's not biology. So it's kind of an arrogant definition, but it's also a quantifiable definition in that you're doing physics if you're trying to predict and measure and analyze. But it leads to a question. Oscar, what do we measure? This year, three main things. We measure time via some kind of stopwatch device. Does anybody know what are the fundamental science units for time? What do we measure time in? Seconds. Not minutes, not hours, not years. Seconds. If they're in the other ones, we'll usually convert them. We measure length. What's the fundamental SI, System International science unit for length? Meters, spelled R-E in Canada, but I'll take either. Oh, other video in the background uploading. And the third thing is mass. Mass. Measured in. It should be grams, but the problem is a gram is so small, the standard unit for mass is the kilogram, which kind of bugs me because the previous two don't have prefixes, don't have the metric prefixes in front of them. It's not kilometers or centimeter, it's meters. It's not kiloseconds or gigaseconds, it's seconds. But it is what it is. A gram is just so small. We started setting up all of our stuff with a kilogram as the standard mass. The system that we use, these units are called SI units. The slang term is the metric system. Last year when I taught this course, I said that there was only 2 countries that hadn't gone metric in the planet, Liberia and the US. Liberia went metric last year around Christmas. The US is the only country that hasn't gone metric. And if you think about the US, that explains a lot about the US, doesn't it? There are 7 and only 7 base quantities in the SI unit system. Everything else that you learn is actually made up of these. These are the 7 that are defined. Everything else is derived from these 7. The first 3 I already told you. Length, meter, time, second, and mass, kilogram. Justin, it is worth learning what units, I was putting those 2 words together, go with what concepts. Trust me, and that's going to be one of the things I'm going to emphasize to you. You want to memorize what units go with what concepts. And by memorize, I don't mean, Spencer, write it out 50 times. I mean, pay attention. You will anyways because you're naturally lazy, but it's a huge time saver if you glance at a number and you see a meters per second squared and it's acceleration. Or you glance at a number and next to it you see newtons and it has to be a force. Or you glance at a number and you see volts and you say it's got to be voltage. That's a fairly obvious one, hopefully. We're going to be memorizing what units go with what. So I'm going to emphasize units. Does anybody know what electric current is measured in? Not volts. Joules, nope, that's the unit for energy, which is defined in terms of these. Good guess, though. You've heard the term. Begins with the letter A. Yep. Louder. Amps. Symbol, capital A. Named after Ampere, a scientist who did a bunch of work with electricity. That one is defined. All the other electric units are based on the definition of that. Temperature. What do we measure temperature in? Degrees, except there's several different scales. There is degrees Fahrenheit, US. There is degrees Celsius, which is the metric system, but which is not the SI standard. There is degrees Kelvin, or degrees lowercase k. I love this unit because my name is Kelvin, spelled that way. In fact, Spencer, when the internet first came on, when Google first was set up, if you Googled the word Kelvin, the first thing that came up was a page dedicated to William Thomson, who is Lord Kelvin, of whom this unit is named after. And it said in huge letters, taking up the whole page, Kelvin is God. It was great. Then Google redid their search algorithm. Actually, to be honest, as much as I'm proud of my name, this is an embarrassment to me because Lord Kelvin, I'm not sure he deserves to have a unit named after him. He did some brilliant work in heat, but his understanding of electricity was wrong, was fundamentally flawed, was fundamentally wrong. But because he was a British lord, a member of the aristocracy, and because, to be honest, he was an SOB, if you disagreed with his understanding of electricity, he ruined you. You can make an argument he set electricity back by 50 or 60 years in terms of its development going out to the rest of the world and all of our infrastructure, because he was wrong. And he had the money and power to expound his wrongness. Amount of a substance. If you've taken Chem 11, and some of you grade 12s have, you've seen this one already. It's also a small animal. Say it loudly.
Moles.
M-O-L. Who's in Chem 11 this year? Okay, so you'll learn about what's called Avogadro's number. Mole is defined in terms of Avogadro's number. A mole is a way to measure an amount of a substance, whether it's a liquid or a solid or a gas. You can still measure it. Oh, just hang on a second. We're going to pause the video for a sec. These first 6 units, they're okay. My favorite is this last one, because the first 6, you don't know how big they are until you've seen them. You don't know how big a second is until you've grown up and you've looked at watches often enough, and now most of you know that 1 second is about that long. But if you haven't seen that, you have no way of knowing. You know a meter is about this long because you've seen meter sticks. This last one, even though you've never heard of it, as soon as I tell you what it's called, you'll all know instantly how big one is. Light intensity is measured in candles. And you now instantly all know exactly how big 1 candle is, don't you? That's what more units to me should be like. They should be stuff that I already know. So 1 candle of brightness is about, yeah, that bright. And I know there's some variation between a really bright candle and a small, but most candle flames are about that bright. Okay. Everything else is derived from these 7. Now, this year, we will use, don't write this down, these. If you take Physics 12, we'll get to that. If you take Chem 11, you'll do that. We don't do temperature much. I think you do it a little bit in Science 8, poorly. We don't do temperature much in physics because really to handle it, you need calculus, because temperature, you may have noticed, if it's a big object and you're heating it up, the outside heats up at a different rate than the inside, which means you have changing quantities. That's what calculus was invented for. It also depends on the shape of the object, how it heats up. That's what calculus was invented for. And light intensity, we don't look at it all here either, but I'm a nerd. I had to show you guys those. So, okay, turn the page. Put your pencils down. I wrote here, in addition to base units, the SI system uses prefix units, what you folks probably called metric units, to assign a multiplying factor, large or small, to the original unit. For example, 2.5 kilograms can be written as 2.5, and then kilo is replaceable with times 10 to the third power. Grams. The prefix kilo means times by 1,000 or times by 10 to the third. It says, complete the chart below. You do not need to memorize these. I gave you the ones we'll use this year on the yellow formula sheet somewhere. Can you find somewhere on that yellow formula sheet? There should be a chart, like, somewhere? Yes? Find it? Y'all know where it is? Okay, what's the smallest value I gave you on there? Did I give you nano?
Pico.
Did I gave you pico on there?
Wait,
On the yellow, sorry, on the yellow sheet. Oh, I went even further. No, smaller. Okay. So, pico, what's the symbol for pico? Well, you know what? Actually, let's start right here. Here's the base unit. This way you're getting smaller. This way you're getting bigger. Let's go smaller. So we have deci. What's the symbol for deci or deci? Just a lowercase or uppercase that matters? Lowercase d, and that means multiply by 10 to the what? -1. That's the same as or divide by 10. I usually just multiply, and that way I only have to, remember to multiply. But multiplying by 10 to the -1, the same as dividing by 10. Centi, this one I know, lowercase c. By the way, deci I almost never use. I would rather say 12 centimeters than 1.2 decimeters, even though they're the same thing. 12 centimeters, I'm so familiar with a centimeter. You tell me 12 centimeters, and I say, yeah, about like that, right? Give or take. So centi is 10 to the -2, yes? Or divide by 100. Milli, lowercase m? No, yes? I'm going from memory, and correct me, because I memorized them over the years, but you don't have to. And it's 10 to the -3. Or divide by 1,000. Micro. Now, unfortunately, we used M for milli, and capital M is used for mega. So micro, we use the Greek letter M. Now the Greek letter M is called a mu, and it looks like this. If you're really wondering what it looks like, have patience for a second. Mu is what? 10 to the -6, yes? Which is divide by, you know what? I'm going to stick with scientific notation. Now the zero, divide, I think it's divided by 1,000,000, but we're getting too many zeros. The scientific notation works much nicer. The exponents works much nicer. Nano, lowercase n, I think is 10 to the -9 we multiply by. And pico, lowercase p, and I gave you a chart with pico on it? Yeah, what's pico? 10 to the -12? So, when I was in high school, don't write this down. This is where we were. We had just designed microcomputers. Do you hear the prefix? Where are we? What do you hear frequently talked about now? What type of technology? You guys are here. You hear about nanotechnology all the time. Although I've just very recently started to hear about pico-sized things. What comes smaller than pico? What else did I give you on your chart? Sorry? Femta. Later on this year, I will show you a femto camera, a camera that takes pictures every femtosecond. That is fast enough to actually take a picture of a beam of light moving. You can actually see the beam of light as it moves. What's after that? Sorry? Acto. You're starting, I think, is there anything after that? Okay, I think acto is when you're starting to talk about smaller than the nucleus, which Okay, there is still room to go, but not much more room to get smaller. Let's get bigger. Deca. Is that one capital D or is that one DA? Never use it. But okay, and I think it's times by 10. Yes? I'm going from memory here. Again, you know what? I'm never going to say 5 decameters. I'm going to say 50 meters. Hecto. H. I never use that one either. It's 10 to the 2, is that right? 100? Instead of dividing, it's timesing by 100. Again, I'm not going to say 3 hectometers. I'm going to say 300 meters. Which one do we use all the time? Kilo. Certainly for kilometers and kilojoules and kilowatts. You know what? That's a useful one. So lowercase k, 10 to the 3rd, or times by 1,000. That's probably the only one that I might say for you guys is worth memorizing, just because you use it often enough, you'll get tired of having to look it up. Carson, you'll get sick of looking at your formula sheet. So if I ever tell you to memorize something, it's not out of you have to, it's out of, trust me, you'll be lazier if you memorize it than you do if you look it up all the time. Mega, capital M, and that's 10 to the 6th, yes? Or times by 1,000,000, but you know what? Now we got so many zeros, I'm just going to stick with the exponential notation. Giga, 10 to the 9th. Tera, 10 to the 12th. Is peta next? What's after tera? Peta. Yeah, Captain Obvious, thank you. And that's 10 to the 15th. And did I go past peta?
Yep.
What's after peta? This one I don't remember. Oh, exa. Exa or exo? Exa? Exa. And I didn't go past that. So, again, don't write this down. When I was in high school, my computer had 64 kilobytes. Wow, it was amazing. 20 years ago, my first ever hard drive had 80 megabytes, and I didn't know how I'd ever fill that. Gigabytes are the norm, but that's probably going to be fading in the next 2 or 3 years, because now if you go buy an external hard drive, what? They're all in the terabyte range. Google has introduced petabytes. Google has talked about their storage centers having X number of petabytes per storage center. And also I'm hearing now the latest computers, when they talk about how many calculations they can do per second, they call each calculation a flop, and we're just into the petaflop, but those are the computers like at the NSA and CIA, those are the fancy smancy crazy, they're there. So peta, probably about 10 years away from entering our common vocabulary. Exa, probably about 20 years away from entering our common vocabulary. I'm that old. Any base unit can be used with a prefix. For example, 1 kilogram is the same as 1,000 grams. So I wrote down here, handy trick. You can replace the symbol, the K, the DE, the capital M, the prefix symbol with the power of 10 that goes with it. You can replace the symbol with the power of 10 that goes with it. So if you want me to convert, for example, don't write this down, 800 millivolts, how many volts? Oh, it's going to be 800 times, milli is 10 to the what? Sorry, micro. I said milli, micro. This is micro, Mr. Dueck. Sorry? 10 to the negative 6. I go to my calculator. I go, okay, 800 times 10 to the power of negative 6. Oh, you know what? Now, I get an answer in scientific notation, and we'll talk about that a little bit later, but this is saying 0.0008 volts. That's 800 microvolts. Turn the page. During this course, we're going to use models, often mathematical, to help us understand a particular set of phenomena. But full disclosure from day one, the vast majority of what I teach you is wrong, is garbage. Because to really be accurate, Kyle, in our three-dimensional world, we need calculus. So we'll look at projectiles, but we'll ignore air resistance. We'll look at forces, but we'll ignore friction. We'll ignore a lot of stuff that make answers yucky. Or if we're looking at a question with ropes and masses, our ropes won't weigh anything, just because that makes the math yucky. So full disclosure, most of what I teach you is going to be wrong. But it's going to be close. Riley, it's going to be close. And sometimes it'll be really close, and every once in a while I'll say, this one is not complicated enough that we can bring in a few extra bells and whistles and do this one right. Since our models will be mathematical, good math skills are a help, a must. Here's a review of the basics. You want to get your calculators out, please? If you don't have a calculator here, it's going to be important that you keep the same calculator and figure out how it works. I will explain to you during the lessons how your calculators work. I will not help you on a test, because if you're asking me how it works on a test, you haven't done the homework, or you brought a different calculator because you forgot your own, and I'll just stand there and make fun of you. I got better things to deal with than that. So, first of all, conversion. I wrote, convert the following distances to meters. 1.1 centimeters. Well, I would go like this. I write down what they gave me. Anytime I'm doing a unit conversion, the very first thing I do is I write down what they gave me. And then I replace the centi with its power of 10. Centi is 10 to the what? And then I go to my calculator. 1.1 times 10 to the power of negative 2. So you need to find where your exponent button is. Usually, if it's a good calculator, it's the thing that looks like a little hat. It's the thing that looks like a Shift 6 on a keyboard. Often, it's over on the right-hand side somewhere, but not always. And see if you can get an answer of 0.011. Now, if you can't find your exponent button, now is the time to ask, and I will help you find it. All right, 76.2. Oh, what was the answer? How about write the answer down, Mr. Dueck? 0.011. Now, sometimes you're going to get answers in scientific notation. We'll talk about that in a couple of seconds. 76.2 picometers. So 76.2 times, what can I replace the pico with? 10 to the... (76.2) times 10 to the negative 12, and I'm getting an answer back in scientific notation. This is now 7.62. When I see an E, that's times 10 to the negative 11. So first I'm going to write that down. 7.62 times 10 to the negative 11. You're going to get really good at scientific notation this year. If you're not already, you will. What does that mean? That actually means 0. What's my exponent on the 10? What's my exponent on the 10? So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 is where I write the 7. 6, 2. And the reason my calculator gives me an answer in scientific notation is it can't fit it on the screen. And if you've forgotten, don't worry, we're going to do a bit more in a second. C, 0.123 megameters. I would go 0.123 times mega. Ten to the sixth. Do you get 123,000? 123,000. Oh, and always put the units. I noticed I forgot to put the units on the first one. That's meters. And I forgot to put the units on the second one. That's meters. I will take marks off on tests for no units. Scientific notation. This scientific notation looks very similar to this, but you don't need to follow this procedure because your calculator has a scientific notation button built in. And if you do it the long way, you're actually going to end up often with an extra 0 in your answer. Anyways, the Earth weighs 5,980, lots more zeros, kilograms. It does. How would I write that in scientific notation? Well, the rule for scientific notation is you always write one non-zero digit, the first non-zero digit. What's the first non-zero digit as I move this way that I run into? 5. A decimal point goes there. You write any remaining non-zeros, 9, 8. But you replace everything with a power of 10 times 10 to the, and then once you've written that, look up. A lot of kids make the mistake, they just replace the zeros. Actually, no, I moved the decimal point from here all the way to here. How many spots is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That number can be written as 5.98 times 10 to the 24th kilograms. Most common mistake is kids just count the number of zeros and say, oh, it's up. No. You have to include the fact that that 9, 8 also got moved back behind the decimal point. That's if you're making a big number into scientific notation. What if you're making a really small number, like example 2? One proton has a charge of, oh, hang on. We need to be able to type this into our calculator. So get your calculators out, those of you that have them. Here's what you will not, here's how you won't do it. You won't go 5.98 times button, 10 button, exponent button, 24. Now that looks right, and that will give you the right answer in very simple calculations. But as soon as we go more complicated, your calculator won't understand what you mean, and you'll get wonky answers. Instead, you're going to find that you have a scientific notation button, and I'll tell you what it looks like in a second. You'll type 5.98, and then here's what you're looking for. You're either looking for a button that says EXP, often in the bottom row. If you have a Casio, that's what you're looking for. If you press that, that includes the times and the 10 and the to the power of. All you need to do is type in the 24. Or you may be looking for an EE button. If you have the TI, the EE button is second function comma. That's for Spencer. Second function that. And it looks like that. Or you may have a times 10 to the power of button. So you need to find your scientific notation button, because to type this, all you do is that. You'll notice I did not press times. I did not type 10. I did not hit to the power of. So find that. If you can't find your scientific notation button, now is the time to ask me. And then just to see what your calculator looks like, if you hit enter, it should show you what scientific notation looks like that. Okay? Let's try for a really, really small number. So 1 proton has a charge of that many coulombs. It does. I would go like this. The first non-zero number, 1, point, any other non-zero numbers, times 10 to the. Now this time I've moved the decimal from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Double check, is it 19 spots? How do I show, though, I don't write this. How do I show that I've gone divided by? Yeah, negative. Okay? Coulombs. If I type that into my calculator, 1.6, scientific notation button, negative 19. Also, by using your scientific notation button, it's faster. Now, somebody said, Mr. Dueck, why can't I go like this? Because that's what you're writing. The problem is your calculator, if you type this, doesn't know that both of those are attached to each other. So if you multiply or divide, it won't know that you actually want to include that 1.6. If you use your scientific notation button, your calculator knows that this 1.6 is glued to the times 10 to the negative 19, and it will treat that as one number. So it's a syntax issue with calculators. I wrote here, let's try some arithmetic. Okay? First thing, how many terms, how many expressions do you see on the top? Two sets of brackets. How many things do you see on the bottom? So if I'm going to use my calculator, I'm going to have to put the top in one big uber bracket and the bottom in one big uber bracket. Second thing, when I handwrite, I show multiplication with brackets. I don't do that on a calculator. Put your calculators down, look up. I would never type it this way. Bracket, bracket, 1.8, scientific notation button, negative 3, close bracket, bracket, 2.6, scientific notation button, 5, close bracket, close off the top, divided by bracket. Can you see it's way easy to lose track of brackets? So I would type it like this. You're all going to type with me. Bracket, pick your calculators up. 1.8, hit your scientific notation button, whatever it looks like. Negative 3. What do two brackets side by side mean mathematically as an operation? Hit the times. That's easier to separate with your eyes than multiple brackets. 2.6, scientific notation button, 5. Close off the top with a bracket. That's saying everything on the top. What's a fraction the same mathematical operation as? Divided by. Is there more than one term in the bottom? Better open up a bracket. 9, scientific notation button, 8, times 1.3, scientific notation button, negative 1. And if you hit enter or equals, and you haven't done any typos, you should get 4 times 10 to the negative 6, or 0.0000004. Now, if you did not, if you had an error, don't clear it. Call me and I'll come look. By the way, if you ever get a wrong answer and you're not sure why, don't clear your calculator. It's almost always a typo, and it's something obscure or weird that I have to show you for your particular brand of calculator. You guys are looking befuddled. Who got different? Okay, don't clear it.
Who did?
So I get 4 times 10 to negative 6. I didn't say close your books. I'm going to in a second. So I'm going to start off. Please make sure you remind me next class. I need to show you the Mega Penny project. There is a video called Powers of 10, but I may work that into another lesson later on as well. Okay? Homework, you have none on the first day, except if you show up on Wednesday without a calculator, I'll be a grumpy bear. Well, I'll probably have you coming after school and I'll beat you upside the head in love. Okay?